All right, so 4.7 is called Steps in Solving Optimization Problems. So this is really one of the best applications of calculus. So our goal is we are going to want to maximize something, or we're going to want to minimize something. So if we take a look at this, it's got some examples of, or a procedure of how we're going to do this. So to solve an optimization problem, the first step, as always, should be to read the problem carefully until it is clearly understood, and ask yourself, what is the unknown, what are the given quantities, and what are the given conditions? And then B, draw a diagram, and that is very helpful because oftentimes, as we had with other application problems, we're going to need to use some geometry or something else to help us simplify the situation. And we need to introduce notation similar to what we did with the related rate problems. We need to assign symbols to the quantities that need to be maximized or minimized. We'll call it Q. And then also select a symbol for the other unknown quantities and label the diagram with these symbols. And it may be helpful to use the initials as suggestive symbols, so A for area, H for height, etc. And if Q has been expressed as a function of more than one variable, then we need to use the given information to find a relationship in the form of equations among these variables. Then use these equations to eliminate all but one of the variables in the expression for Q, and then Q will be a function of one variable. And then we need to find the domain of this function. And then finally, after doing all of that, we're going to use the methods from section 1 and section 3 to find the absolute maximum or absolute minimum of the function. And if the domain is closed, then we need to use the closed interval method, which means we also need to remember to test the endpoints, because local maxes and local mins occur at critical numbers, and then on a closed interval we can also have a max or a min at the endpoints. All right, so we're going to start off with the most classical optimization problem ever. So, example 1. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a cliff. She needs no fence along the cliff. What are the dimensions of the field that have the largest area? So let's start with our diagram. All right, so let's start by drawing a diagram. And our diagram, here's our cliff. And then we have our fencing. So we need to label each of these quantities. So for no reason other than I feel like it, I'm going to call this the length, and I'm going to call this dimension the width. When we're working with these types of problems, we're going to have two things that we need to identify, and I'm going to call one of them our objective function, and this is what was referred to as Q in that list above, and the objective function is what we're trying to maximize or minimize. So we want to find the dimensions of the field that have the largest area. So our field is a rectangle, so its area formula is going to be length times width. So then we're always going to have some sort of constraint. And this is going to be our constraint equation. And this is what limits us from just making the largest, or making the field infinitely big. So what's the resource that we have that's preventing us from making this as big as we want? Well, that's going to be the amount of fence, right? So our constraint equation is going to be 2L plus W is equal to how much fence she has, which is 2,400 200 feet of fence. All right, so now we have our objective function and we have our constraint equation. So what it was talking about is when we were doing this, we have our diagram, we have our stuff, and then we have Q has been expressed as a function of both L and W. So what we need to do is we're going to solve our constraint equation for one of these two variables and substitute it into the other. So in this case, I'm going to solve for W. You will get the same answer in the end if you solve for L, it doesn't matter. So either one of these will give you the same thing. So 2400 minus 2L is what W is. And then what we do is we are going to substitute this into our objective function. That gives us Q is equal to L times 2400 minus 2L. So now we have our objective function expressed as a function of just one variable, L. So now the first thing we need to do is talk about the domain. And when we're talking about the domain here, we're not talking about the mathematical domain. Because if I were to multiply all of this out, I would get negative 2L squared plus 2400L. Well, this is a polynomial, so what would be its domain? All real numbers, right? But we have to take into account what it is we're talking about, which is, in this case, we're talking about the area of a field, right? So what's the smallest area that we can possibly have? Well, this is just like height. I can't be negative 2 feet tall, and a field can't have a negative area. So the smallest possible area is going to occur at 0. So that's going to make our domain start at 0. And then what is going to be the maximum L value for our domain? Well, our constraint equation can help us out there, because if we look over here, we know that W has to equal 2400 minus 2L. Well, what's the biggest L could possibly be? Well, because W has to be positive, so if L is 1200, 2 times 1200 is 2400, and 2400 minus 2400 is 0. So that gives us that the domain, or the feasible domain of this problem, is from 0 to 1200. If we checked any values outside of that, we would see that Q would have negative values. And since area can't be negative, it's not going to be in the domain. So those are our endpoints for our domain. So now we want to find the maximum of this. So we take our derivative. So Q prime is going to be equal to negative 4L plus 2400. So then to find our critical numbers, we're going to set that equal to 0. So we have negative 4L plus 2400 is equal to 0. When we minus 2400, we minus 2400, and we get negative 4L is equal to negative 2400. We divide by negative 4, we divide by negative 4, and we get L is equal to 600. So that gives us our critical number, and then we need to determine if it's a max or a min. So we can either use the first derivative test or the second derivative test. The second derivative test is definitely easier this time, because what's Q double prime going to be? Well, the derivative of negative 4L is just negative 4, and the derivative of a constant is 0. So this tells us that our graph is always concave down. Well, if our graph is concave down, that means it looks like this. So then, at our critical number, are we going to have a max or a min? Well, if it's concave down, the second derivative test tells us it has to be a max. So we are going to have a maximum at L equals to 600. So to find the value of that maximum, we're going to plug this back into our objective function Q. But since we have a closed domain, we also need to check 0 and 1200. So if we do q of 0, and I'm just going to put the objective function in my calculator to help us optimize this. So I have x times 2400 minus 2x. And if I go y of 0, I get 0. And I need to test 600, so we put in 600. Oh, that's not the right number. We put in 600. And that gives us 720,000. And then lastly, if we plug in 1200 once again, we're going to get 0 once again. So it appears that at 0 and 1200 we got the absolute minimum, which is 0 area, and then we had the maximum occurred at 600, which gave us 720,000 square feet. So let's go look at each of these. So we had our L. So in each of these situations, what happened? Well, if L equals to 0, what happened in our diagram? We built the fence just right next to the cliff, so there was no area. In the second case, 600, that's where we got the maximum. And then in the last case, when we made L equal to 1200, what did we do? We built two parallel fences next to each other with no space in between, and once again got a field with area 0. So we indeed got both our absolute minimums and the absolute maximum of that function. And the only one that we were really interested in was the one at the critical number, which was the area of 7,200. So we haven't quite answered the question. So we know these two things. The max area is 720,000 square feet, and we know that the length, L, is 600, but what would the width be? Well, there's a couple of different ways we can get the width. We could just plug into this formula right here, because that's our formula for the width. So 2400 minus 2 times 600 tells us that the width is 1200, or we know that the area formula for a rectangle is area is equal to length times width. So then that would mean the width would have to be equal to 720,000 divided by our width, or our length would give us our width, which also gives us 1200. So then the width is 1200. All right, so it looks like yeah, it looks like we're all back. So did it boot you guys back into this room? Yes. Okay. It said, hey, come back. Okay, perfect. All right, well, that worked pretty well. All right, and we're all seeing my screen, so let's just go over this. I'm 100% positive we all got it, but let's do this. So we have our objective function. In this case would be length times width, and our constraint, at least in the way I drew the diagram, and if you drew it the other way you get the same answer. We have that our perimeter of 300 would be 3w plus 2l. So if we solve that equation for L, we get 300 minus 3W over 2 is equal to L. So then our objective function is Q equals L, so 300 minus 3W over 2 times W, which gives us 150W minus 3 over 2W squared. So we find our critical number by taking Q prime, which gives us 150 minus 3W. And we set that equal to 0 and solve for our W. So we add 3W, we add 3W, we get 3W equals 150. Divide by 3, and we get W is equal to 50. So then, if we have W is equal to 50, we can put that back into either one of our functions. So we would have 50 times 300 minus 3 times 50, all divided by 2. And I'm missing a 0. I'm like, it shouldn't be negative. Helps if you type correctly, not 30. 300, and we get 3,750. So then that tells us that the area is 3,750 square meters. So then to find our length, we would divide that by 50. And we would get L is 75, and W, which we found at the critical number, was 50. And if we tested either of the endpoints, we found that those were both of the extreme values that gave us 0 for our area. All right.
Professor?
Yes?
I think the thing that I did wrong for this problem was for my objective, and I did 3L times 2W. Like I did. Like, what was wrong with that?
With 3L plus 2, nothing. For your constraint?
For the objective one. 3L times 2W.
Okay, so for the objective function, remember the objective is what we were trying to find, and we wanted to find the maximum area. So our objective function had to be the area of a rectangle.
Of the bar?
Yeah, of the pens, right? Because that's what we were trying to find the area of.
Oh, so you didn't consider them like two separate pens?
Well, I did, because what's the area of one pen? L times W. But it's interesting because calculus doesn't care. If you did both of them, it would be 2 times L times W, right? Because this width is 2L, or that dimension right there is 2L. If you go through and do the calculus with the derivatives, you'll get exactly the same answer.
Okay, well, we got it wrong because we did a different objective function.
Yeah, that'll get you. So the constraint is what's keeping us from making the objective function as big or as small as we want, whereas the objective function is what we're trying to find the maximum or minimum of. So let's take a look at our next example, and we'll try to identify both the objective and the constraint. So let's take a look at this, and I think it'll be good to illustrate the point that we're talking about right here. So example 2 says, find the point on the parabola y equals x squared over 2 that is closest to the point 4, 1. So let's draw a picture. So we've got a parabola, y equals x squared over 2. So it's going to look something like this. That's our parabola. And then we have some point, 1, 2, 3, 4, 1. And what's our objective? We want to find the point on the parabola that is closest to this point. So now imagine we have some point x comma y on this parabola, and we want to find that point that is closest to this point. So what's our objective? Well, our objective is we want to minimize the distance, right? So what do we know about finding the distance between 2 points? Well, we have our distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. So that's our objective. And then we have our constraint. Well, what's constraining us in this case? And what I mean by that, well, what's keeping us from taking that point x comma y and just moving it to 4 comma 1? Well, it has to be on the parabola. So what do all ordered pairs on the parabola have to look like? Well, we have the equation of the parabola is y equals x squared over 2. So that's our constraint. So now we want to find the distance between these 2 points. And we have the point 4 comma 1 down here. And we have this. Well, if we have x comma y as a point, that's going to be, we have x, but then what's our corresponding y value? Well, what is y the same as? X squared over 2. So if we substitute that into our objective function, we have the distance d is equal to the square root of x2. So that's x minus x1, which is 4 squared, plus y2, which is our x squared over 2, take away 1, quantity squared. And this gives us our function that we need to find the minimum of. So right now we would need to take the derivative of this, and that's going to be chain rule plus chain rule if we need to do it that way. But it turns out that there is a useful fact that we want to take advantage of. The critical numbers of the square of the distance function are the same as the critical numbers of the distance function. So this fact means that when we're trying to find the critical numbers of this, we can just minimize or find the critical numbers by essentially ignoring the radical, which makes the calculus a lot simpler. If you do it the other way, you will get exactly the same thing. You'll just work a lot harder to get those critical numbers. So now, let's go ahead and find Q prime. So Q prime is equal to 2 times x minus 4 plus, I guess I should be explicit. So by the chain rule, we bring the 2 down in front, times x minus 4, times the derivative of the inside is 1. Now we take the derivative of the second one, our 2 comes down in front. We have x squared over 2 minus 1 times the derivative of the inside. So the derivative of x squared over 2 is 2x over 2, and the derivative of 1 is 0. So then cleaning that up a bit, we get q prime is equal to 2x minus 8. So we distribute that in. These reduce out, so the 2 and the 2. And then if we distribute in our 2 and the x into our parentheses, we get 2x times x squared over 2 gives us x cubed, and 2x times minus 1 gives us negative 2x. So then a miracle happens. Those two things reduce out, and finally, after all of that, we end up with x cubed take away 8. So we now need to solve that polynomial equation. So we have x cubed minus 8 equals 0. And you may or may not remember, but that is the difference of cubes. And our formula for factoring the difference of cubes is, if I have a cubed minus b cubed, it's a minus b times a squared plus ab plus b squared. And something that's useful to remember is that when we use this formula, the quadratic trinomial will have no real solutions. So our only critical number is going to come from that very first part. So we factor this, and we're going to have x minus 2 times x squared plus 2x plus 4 is equal to 0. And if you checked this, as I just mentioned, using the quadratic formula, you'll discover that you get two complex or imaginary solutions. So then our only critical number comes from x minus 2 equals 0. So we add 2, add 2. So our critical number is at x equals to 2. So then to find the corresponding point on the graph, we're going to use this function. So then we would have y is equal to 2 squared over 2, which just gives us 2. So the point on that parabola that is closest to the point 4, 1 is 2, 2. So if we were to, my parabola is terrible, because it doesn't actually go through the right point, but if we found the point 2, 2, and we did a graph, that would give us the point that is closest. And yeah, I didn't put a graph on here. That is closest to that point. All right, so this one was a little bit different, but it follows the same basic formula where we have an objective function and we have our constraint. We substitute the constraint into the objective, we take the derivative, and we get that. And we see from our picture here that there's only going to be a minimum distance, because if I just let x go to either positive or negative infinity, I'm going to get as far away from the point 4, 1 as I possibly want to be. All right, so let's take a look at our next example. So example 3 says a cylindrical can is to be made to hold 1 liter. The material for the top and the bottom cost 15 cents per square centimeter, and the material for one side costs 5 cents per square centimeter. Find the dimensions that will minimize the cost of the metal to manufacture the can. And then we're given the hint that 1 liter is equal to 1,000 cubic centimeters. And that's because in the MKS system, we have that 1 milliliter is the same as 1 cubic centimeter. And there are 1,000 milliliters in 1 liter. All right, so let's draw a picture. So our goal is we want to make a can. So there's the top of our can. And we have something that looks like this. And let's label it. So we have a circle on the top and the bottom, and we don't know what they are, so we're going to have a radius of r. And then we have a height of our can, which gives us this. So then our goal is to do what? We want to find the dimensions that will minimize the cost. But we know the cost per unit area, so the cost per square centimeter. So let's imagine that we could cut this can up into its different parts as if we were trying to manufacture it. So the top and the bottom are both going to be circles of radius r. And then if we cut the side, it's going to look like this. If we cut the side and lay it out flat, we know its height is going to be h, but what is the length of this, or the width of this side, going to be? Well, that side has to fit around the edge of the circle, right? Because we got these circles from putting them on the top and the bottom of this, so that means that dimension has to be the same as the circumference. And the circumference of a circle is 2 pi times r, where r is the radius. So then we can now calculate the area of each of these things. So the area formula for a circle is pi r squared. So then the top and the bottom, we have 2 circles, so its area is going to be 2 times pi r squared, because they each have an area of pi r squared. And then the area of the lateral side of the can, well, when we lay it out flat like this, it's a rectangle, so its area is going to be 2 pi r times h. So now we know the area of the top and the bottom and the area of the side. Our objective function is we want to minimize the cost. Well, our cost is going to be equal to the cost of the top and bottom plus cost of the side. But to calculate the cost of the top and the bottom, we know the cost for the top and the bottom is 15 cents per square centimeter. So it's going to be, this one is going to be the cost per square centimeter times the area. And we're going to get the same thing here, where it's going to be the cost per square centimeter times its area. So our cost per square centimeter for the side is this. And now we're going to put all of these things into our formula to get our objective function. So our cost per square centimeter for the top and the bottom is 15 cents. So we're going to have $0.155 or $0.15 per centimeter squared times our area. And the area of the top and the bottom is 2 times pi r squared. Plus our cost per centimeter for the side is 5 cents, so $0.05 per square centimeter times the area of the side, which is 2 pi times r times h. So that gives us our cost, and we can simplify that up a bit if we want. So we're going to have our cost. 2 times 0.15 is 0.3 pi r squared, and then that's going to be dollars per square centimeter, plus 2 times 0.05 gives us 0.1 pi RH, and that is also dollars per square centimeter. So that's our cost function, but now we need our constraint. And what's constraining this situation? Well, our constraint is right here. What has to be the volume of our can? 1 liter. So our constraint is that our volume has to be 1 liter. And our hint told us that 1 liter is equal to 1,000 cubic centimeters. So now the volume formula for a cylinder is the area of the base, so that's pi r squared times its height. So then that gives us that 1,000 cubic centimeters is equal to pi r squared times h. So now we need to solve this for either r or h. Personally, I think it's easier to solve for h. So h is going to be equal to 1,000 divided by pi r squared. And then if we substitute this into our equation, we get that our cost, so Q, is going to be 3 pi r squared, or 0.3 pi r squared, plus 0.1 pi r, and then our h is 1,000 over pi r squared. So we simplify that up a bit. Our r's reduce out, our pi's reduce out, and 1,000 times 0.1 is going to give us 100, so we get 0.3 pi r squared plus 100 over r. And that is our objective function. We take its derivative, so q prime is 0.6 pi r plus the derivative of 100r, we can write it as 100r to the negative 1. So if we take its derivative, we're going to get negative 100 r to the negative 2. So kicking the r back into the denominator, we get minus 100 over r squared. So now we set this thing equal to 0. We get 0.6 pi r minus 100 over r squared equals 0. And it's a rational function, so we clear our fractions by multiplying everything by r squared, giving us 0.6 pi r cubed minus 100 is equal to 0. So this is cubic in r again. This time I'm going to solve by using the cube root to get our real solution. And we get r cubed is equal to 100 over 0.6 pi. taking the cube root of both sides gives us r is equal to the cube root of 100 over 0.6 pi. So now we can approximate that. So we press math to get our cube root, that's choice number 4, and the cube root of 100 over 0.6 pi, oh, not e, gives us 0.37575, so if we round to the nearest hundredth, we would get 3.76 centimeters. So that gives us that r is about 3.76 centimeters. So then, to find h, we can use this formula. So h was equal to 1,000 divided by pi r squared. So that's 1,000 divided by pi, and then cube root of 100 over 0.6 pi squared, but that's already in our calculator. So we can calculate that by just going alpha y equals, and we put in our 1,000 in the numerator, and then divided by pi times, and then we get our answer by going second and our negative key squared. That way we don't have to type it out or approximate, and we get this value. So then that gives us that the height, rounding to 2 decimal points, would be 22.55 centimeters. All right. So in the interest of time, because the U-tries are taking a bit longer than they would when we were in class, we'll have to circle back to that U-try, but I really want to show you example number 4. So example number 4 is, a man launches a boat from point A on the bank of a straight river, 3 kilometers wide, and wants to reach point B 8 kilometers downstream on the opposite bank as quickly as possible. If he can row 6 kilometers per hour and can run 8 kilometers per hour, where should he land to reach B as soon as possible? Assume the speed of the river is negligible compared to the speed he rows. All right, so let's draw a picture of this situation. So we've got a river. Looks something like this. And we have point A and we have point B. We know that the width of the river is 3 kilometers. And we know that the total distance from A to B, well, the perpendicular distance, so this distance is 8 kilometers. So the idea then is the guy is going to hop in his boat, and he's going to row to some point on the opposite side, and then he's going to run from that point to point B. All right, so let's see if we can figure out what our objective is. So we want to reach B as soon as possible. So we want to minimize the amount of time it takes him to get from point A to point B. So then our objective function Q is going to be his time on the river plus his time on land. And we want to make this as small as possible. All right, so to do this, we need to figure out, well, how long is he going to be on the river and how long is he going to be on land? To help us, we have our following equation that distance is equal to rate times time. If we solve that for t, it says that time is equal to distance divided by rate. So then using this, his time on the river is going to be the distance on the river divided by his speed on the river plus his distance on land divided by speed on land. All right, so now we need to figure some of these things out. So we come back up to our diagram, and if we call this point X, and we call this point 0, then B is going to be located at 8. Well, this distance from here to here is then going to be X, and what would this distance from here to here be? Well, if the whole thing is 8, we already went X, then this distance has to be 8 take away X. So his distance on land is going to be 8 minus X, but his distance on the river is going to be the hypotenuse of this triangle right here. Well, our triangle has legs X and leg 3, so then this is going to be, by the Pythagorean theorem, x squared plus 3 squared is 9. And that's our Pythagorean theorem. So now his distance on the river is going to be the square root of x squared plus 9. And his distance on land is going to be 8 minus x. And luckily, we know each of those speeds. So he can row at 6 kilometers per hour, and he can run at 8 kilometers per hour. So putting all of this into our function down here, his distance on the river is going to be the square root of x squared plus 9 over his speed on the river is 6 kilometers per hour plus his distance on land is 8 take away x, and his speed on land is 8. So we can simplify that up just a little bit when we get the square root of x squared plus 9 all over 6. Doing some term-wise division here, we get negative 1/8 x plus 1. Because 8 goes into 8 once, and negative 1 divided by 8 is pardon me, negative 1/8. So now we take our derivative to find our critical numbers, so q prime, and we remember that this is x squared plus 9 to the 1/2, so we have 1/6, pulling that out, and then we take our derivative, so then we get times 1/2, and we have x squared plus 9 to the negative 1/2 times the derivative of the inside, which is going to be 2x, minus the derivative of 1/8 x is just 1/8, and the derivative of 1 is 0. So a few things cancel out. The 1/2 and the 2 reduce out, and we get q prime is equal to, in the numerator, all that's left behind is x over, and then in the denominator we have 6. Moving this into the denominator, it becomes a positive 1/2, so it goes back into a square root, x squared plus 9 minus 1/8. So we set this equal to 0, and we need to solve. So we have x over 6 square roots of x squared plus 9 minus 1/8 is equal to 0. We clear our fractions by multiplying by 6 times the square root of x plus 9, which is our LCD. So in the first one, all the denominators reduce out. In the second one, the 6 and the 8 are going to reduce to 3/4. So 0. Then we need to solve this radical equation. So we're going to add 3/4 the square root of x squared plus 9 to both sides. And that gives us x is equal to 3/4 the square root of x squared plus 9. Now we square both sides, and that gives us x squared is equal to 3/4 times 3/4 is 9/16, times, we square a square root, it cancels out, so we get x squared plus 9. So now we open our parentheses by distributing, and we get x squared is equal to 9/16 x squared plus 81/16. We minus 9/16 x squared. We minus 9/16 x squared, giving us, make that 16/16. 9 take away 16 is 7x squared over 16 is equal to 81/16. And we divide by 7/16, divide by 7/16, which means we multiply by the reciprocal, and that gives us x squared is equal to 81/16 times 16/7, so we get 81/7. Finally, we take the square root and we get x equals plus or minus square root of 81 is 9, square root of 7. And we're going to reject the negative square root because it doesn't make sense in terms of our problem. Because if we look at our diagram, he's not going to move away from point B and then run back towards it. That wouldn't make any sense. So our critical number is positive 9 over the square root of 7, or if we rationalize the denominator, 9 square roots of 7 over 7. And if we check by putting this into our original function, we come back to this, and we need to check the two endpoints of our domain. So the domain is he either goes directly across the river, so x equals 0, or the other possibility is he just rides the river directly from A to B, in which case x would be 8. So we need to check x equals 0, x equals 9 square roots of 7 over 7, and x is equal to 8. So if we put the original objective function back into our calculator, so our objective function was this guy before we took the derivative. So we have a square root of x squared plus 9 over 6 minus x over 8 plus 1. And then we need to check these values. So alpha trace, put in 0. Alpha trace. 9 square roots of 7 over 7. And we get this. And lastly, I better clip that though. And lastly, we put in 8, and we get 1.42. So now we pick the smallest one out of that list, and we see that it would be in the middle at 9 square roots of 7 over 7, which is approximately, so 9 times the square root of 7 divided by 7 gives us 3.4-ish. So he'll minimize his time when he lands 3.4 kilometers downriver. If he boats straight across the river, it's going to take him an hour and a half. If he does at 3.4 kilometers downstream, it's going to take him 1.33 hours. And if he just rows directly there, it's going to be 1.42 hours. All right, so we're going to go ahead and stop there.